Section 6.2 talks about the standard normal distribution. We've looked at normal distributions before, and remember, this is where you have a shape for the distribution of your data that looks like this. It's symmetric and bell-shaped. That's what defines a normal distribution. We said that the mean is always in the center of the distribution. That's the most common value. In standard normal distributions, the mean is equal to 0 and the standard deviation is 1. So when we move out one standard deviation along this x-axis here, we will actually be moving out along integers 1, 2, 3, -1, -2, -3. Now, the relationship between the percentage of the area that's under the curve and how far away you are from the mean remains the same as it did with previous sections. If we move out one standard deviation away from the mean, what percentage of the data falls within that range? 68. 68% of our data lies within one standard deviation of the mean. If we go out two standard deviations, what percentage of our data lies within two standard deviations of the mean? 95. And then if we go out three standard deviations from the mean, 99.7. You got it. So that 68, 95, 99.7 rule is still there whether we have a normal distribution with different means and standard deviations or a standard normal distribution where the mean is 0 and the standard deviation is 1. Whenever we have a standard normal distribution, and instead of finding the probability that, say, x is greater than some number, we would use for our variable z. So z is the variable of choice whenever we're talking about a standard normal distribution. Do you remember the formula for how to find z-scores if you know the mean and the standard deviation? Z is equal to your data value minus the mean divided by the standard deviation. And we'll revisit this concept again in 6.3. In 6.2, we're just going to look at working with the standard normal distribution. We're also going to drive home the concept that probabilities correspond to the area under the curve. And this uniform distribution does a good job of driving home that concept. A uniform distribution, remember, is a distribution where we don't vary the height of the distribution at all. It would be something that looks like this. So if we wanted to graph the probability of rolling a number on a die, we would go out from 0, 1, 2, 3, 4, 5, 6, and the height there would be 1, 6. So that the area under the curve, this density curve, is equal to 1. That's one of the conditions that must be satisfied. The total area under the curve must be 1. And then every point on the curve must have a vertical height that is 0 or greater. Well, that means that you can't have any negative values for x. With a uniform distribution, the probability of all the possible values of your data would be equal. Now, hopefully this reinforces the connection between area and probability. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. Remember, the probability of the sample space, which is the total possible outcome for everything that we're studying, the probability of the sample space is equal to 1. And since the total area under the curve is equal to 1, that creates this correspondence between these two concepts. And we can use that then to help us find probabilities. We can use area to help us find probabilities. Here's the graph of a uniform distribution where the shaded area represents the voltage levels greater than 124.5. This is the voltage, and the probability, notice it goes from 123 to 125. That's a distance of 2. So the height of our uniform distribution, because the area under the curve has to be 1, the height then has to be a half, because 2 times a half is 1. The area of a rectangle is length times width. So that's how you come up with this probability distribution. So in this problem, we're asked to find the probability that a randomly selected voltage level is greater than 124.5. That means that what we want to do is find the area of this shaded region, because the area of the shaded region corresponds to the probability that we're looking for. So how do you find the area here? For a rectangle, it's length times width, or in this case, length times height. The length here is going to be the distance along the bottom here, a half, and the width is, or the height, is 0.5, and 0.25 times 0.5 is, so that means that the probability of whatever this situation is of getting this voltage between 124.5 and 125, that probability is 12.5% or 0.125. So on a uniform distribution, in order to find the probability, we just use the formula for the area of a rectangle. This only works with the uniform distribution. For other distributions, we have to use technology. So here's a standard normal distribution. The standard normal distribution is just a normal distribution with a mean of 0 and a standard deviation equal to 1. The total area under the curve has got to be equal to 1. You could use your graphing calculator to graph this curve if you used the function from 6.1, this function right here. You could graph this function. I'm not going to take the time to do that, but this function actually is how you come up with this curve. And how we're going to find the probabilities when we're given z-scores is by using our graphing calculators. There is a table that came with the book, but because I did not require everybody to purchase the book, I'm not going to use the table in order to find probabilities. We're going to use our calculators because technology is strongly recommended. Now here's an example problem that's going to help us figure out how to use the technology. It says a bone mineral density test can be helpful in identifying the presence of osteoporosis. The result of the test is commonly measured as a z-score, which has a normal distribution with a mean of 0 and a standard deviation of 1. A randomly selected adult undergoes a bone density test. Find the probability that the result is a reading less than 1.27. I'm not a medical expert, and I don't know at what level all of these indicators are, that you have osteoporosis, but I do know how to find the probability that the z-score is less than 1.27. Whenever you're working these problems, you want to draw a picture. Draw a normal distribution as best you can. Because this is a standard normal distribution, the mean is going to be 0. We're interested in finding a result with a reading less than 1.27, so 1.27 is going to be over here, slightly further away than 1 standard deviation, so there's 1.27. Now, do I want to shade the area to the left of 1.27 or the area to the right of 1.27 in order to get the reading that's less than 1. Less than is to the left. So we're looking for the area of this shaded region right here. Now, how we do this on our calculators is we go to our calculators, we hit second distribution. Remember, that takes us to our distributions here, and we're looking at the normal CDF. That's number 2. The normal CDF. CDF stands for cumulative distribution function. It's the values that accumulate from the left-hand bound to the right-hand bound. And we hit enter. And we end up with a screen that looks like this. The first number we put in is our left bound. Since this is going off to negative infinity, I just need a really small number. How about negative 100? That's small in the world where the mean is 0 and standard deviation is 1. The right bound then will be what? That's the 1.27. Now normally we would do the comma the mean and comma the standard deviation, but the default setting on your calculator is the standard normal distribution. So if you're using a standard normal distribution, you don't have to put anything in, just the left bound and the right bound. So this, when we hit enter, gives us the probability of the results of a bone density test being less than 1.27. So this number right here means this is the probability of getting a result less than 1.27. The way we would write up the problem that we just did symbolically is the probability that z, it's a z-score because it's a standard normal distribution, is less than 1.27 is equal to 0.89, we'll call that 8, rounding to 3 decimal places. Typically we use 3 or 4 decimal places for the probabilities. If you're using my math lab, there'll be a statement underneath the box where you type in your answer. It tells you how many decimal places to round to. So with the normal CDF, once you get this on your home screen, you're going to type in your left bound, and it has to be a number, comma, and then the right bound. Now this only works, and then you hit enter. This only works with the standard normal distribution. If you have any other mean or standard deviation, you've got to type in the mean and the standard deviation after your left and right bound. All right, let's continue this example problem. It says using the same bone density test, find the probability that a randomly selected person has a result above -1, which is considered to be the normal range of bone density readings. How do we begin the problem? Draw a picture. Draw a normal curve. Zeros in the middle. I always put the 0 in the middle because it gives me a point of reference for putting down the number that I'm going to use, the z-score here. The z-score that we have now is -1. And do I shade to the left or to the right of the -1? To the right, because that's the probability that I have a z-score greater than -1. So what we're looking for then is the probability that z is greater than -1. So we're going to go to our calculators again. Since you already have this on the home screen, the easiest way to get this back is just hit second enter, because that was the last thing I typed in. And then I can just type over the numbers that I put in there. I have -1, comma, need a right bound. It's going off to infinity. We can just type in a big number, close the parentheses, and then I'll just delete out what's there, and we end up with a probability of 0.84. And remember, this is the normal range, so we want this to be a fairly high probability. I'm okay with that. So this probability is going to be 0.841. All right, now a bone density reading between -1 and -2.5 indicates that the subject has osteopenia. Find this probability. Once again, start with the graph. So we draw a picture for a normal distribution. Mark the 0 just so you get a point of reference. And then we're interested in finding the probability that we're between -1 and -2.5. So we shade this region in between those z-scores. And the way we write this up symbolically is we're looking for the probability that z is in between -2.5 and -1. On our calculators then, I'm going to hit second enter, and we go from -2.5, comma, -1. We have a left bound and a right bound, and then hit enter. So if you get an error message, one of the mistakes you may find is that instead of typing in the negative key right here, you may be hitting the subtraction key. That would generate an error. So look for that if you are getting an error on your calculator. So this probability is 0.152. So if you're given the left bound and the right bound, you don't have to make up really large numbers or really small numbers. Now the notation that we use, the probability that z is in between a and b. That's what we use whenever we are given values for a and b. And it doesn't matter where those values for a and b fall on the graph. You still want to draw the graph that goes with this probability. Always draw the graphs in these problems. And your a will always be to the left of b. And your b could be right here. And that means that you're trying to find the area of this shaded region. On your calculator then you would type in normal CDF a, comma, b. If we're looking for the probability that z is greater than a, because it's a z-score, we know we're talking about a standard normal distribution. We would draw a graph. Here the probability that a is greater than 0. We would type in the normal probability. The normal CDF. And we would go from a to, for a standard normal distribution, 100 is a really big number because we're 100 units away from the mean. You can use 100, 1,000, 10,000. Just pick a really big number. To find the probability that z is less than a, draw your graph. I can still use the same a, but now I'm looking for the area that's to the left of a. And on my calculator, I would do normal CDF. Now I'd use a really small number for my left bound, and a would be the right bound. Now what if we know the probability and we want to find the z-score? Well, here's the steps we're going to follow if we know the probability and we want to find the z-score. The first thing you're going to do, always, 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 is draw your picture. Draw a bell curve and then identify the region under the curve that corresponds to the given probability. If the region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. For example, if I wanted to find the area over here to the right, my calculator is going to use the probability over here. And this area is going to be 1 minus the area to the right. This is wrong. This right here is not normal CDF. That should be inverse norm. So when the command appears on the home screen, what you're going to type in is the area to the left of the z-score you're looking for. Sorry, I was in a hurry when I made out these lecture notes. I will have to fix that for later lectures. Alright, finding z-scores when we're given the probabilities. We're going to practice doing what the steps above just indicated. We want to find the z-score here that separates the bottom 95% of the data from the top 5% of the data. So what we're going to do is get our calculator out. We're going to hit second vars again to bring up the distributions. Now this is the distribution that we want, the inverse norm. And with the inverse norm, we're going to type in the area to the left of the z-score that we want to find. So inverse norm of 0.95, and that's going to give us 1.645. Typically, we round z-scores to only 2 decimal places, but when this number right here is almost exactly halfway in between a 4 and a 5, we're going to go out 1 more decimal place and call that 1.645. So this is 1.645. So that's the z-score that's for the 95th percentile. Let's continue this example. It says using the same bone density test, find the bone density scores that separate the bottom 2.5% and find the score that separates the top 2.5% of the population. How do we begin any problem? Draw a picture. So we're going to draw this picture for the distribution. Zero's in the middle. And what we're wanting to do is find this z-score right here that separates the bottom 2.5% from the top and the top 2.5%. So this area right there is 0.025 and this area right here is 0.025. So on our calculators, what we would want to do for this area on the left is type in inverse norm, and what number would I put in the parentheses there? 0.025. And over here on the right, I want to find out inverse norm. What? Do I use 0.025 again? It would be 0.975. Where did I get the 0.975 from? It's everything to the left. So the total area under the curve is 1. If we subtract off this 0.025, then that means the area to the left here is 1 minus 0.025 or 0.975. So let's grab our calculators, clear it out. We're going to hit second enter, 0.025, and second enter, 0.975. Well, look at there. What do we notice about these numbers? Anything? They're the same except for the sign. Are we surprised by that? Or does that make us remember something? There's symmetry there with that graph. So if the area to the left is 0.025 and the area to the right is 0.025, and there's symmetry, meaning if I folded this graph in half along that line right here at the middle, at the mean, then these two numbers have to be the same. They just differ by a sign. So this number right here is negative 1.96, and this number over here is positive 1.96. Well, this has some interesting implications for us. You guys kind of hesitated when I asked you what number is it that we put in right here. Well, if you don't want to figure out what that number is, you just plug in the number that you're given for the area to the right and know that you're going to get a negative number and just make it positive because of the symmetry. Every number to the left of 0 is going to be negative, and every number to the right of 0 is going to be positive z-scores. To get the 0.975, we took the total area under the curve, which is 1, minus the area that was to the right, 0.025, and that gives us the area that was to the left of this z-score. It gave us the area. This right here gives us the area that was over here. Does that make sense? Because the total area under the curve was 1. Does that help? So because of symmetry, these numbers are the same. For the standard normal distribution, a critical value is a z-score that separates the unlikely values from those that are likely to occur. This z-score right here, the negative 1.96 and the positive 1.96, they separate the middle 95% of the population that we consider to be usual values from the outside 5% that we consider to be unusual. We call that number, that 1.96, a critical value. So the expression z sub a denotes the z-score with an area of alpha to the right. So that z sub a, that critical value that we just came up with, would be z sub 0.025, and that was 1.96. Earlier we found a z sub 0.05, and we said that was 1.645. Actually, we found the negative version of it, but the positive version, same number, different sign. So here we're asked to find the value of z 0.025. Let's use our calculator. We just found this one, but let me show you something with the calculator. We know this is going to be a positive z-score because that 0.025 represents the area that's to the right. What this means when I draw the picture is I would have my normal distribution. Some are better than others. And the area to the right here is going to be 0.025. That area is equal to 0.025. The z-score, in order to get it, I know I'm going to have to get a positive number because I'm to the right of 0. But on my calculator, if I just typed in inverse norm 0.025, remember I got a negative 1.96. This number's got to be positive, so it could just, using what I typed in earlier about the signs and the symmetry, we know that this is going to be positive 1.96. Let me just write in another problem. Find z sub 0.01. This is the critical value that would correspond to a 98% confidence interval. You don't know what confidence intervals are yet, but hopefully when we get to them, this will come back to you. How would you find this number on your calculator? Which one of these distributions would I use? Number 3, the inverse norm. And what would I type in? 0.01. And I end up with a negative number. Is this critical value going to be negative? No, remember, this is the area to the right. I didn't draw my picture, that's why it gets confusing. You draw your picture, and then you can see that I've got this area to the right that's teeny tiny, 0.01, and I'm looking for the z-score. Is it going to be positive or negative? There's 0 right in the middle. This is a standard normal distribution. It's got to be positive because it's the number to the right of 0. 0 on a standard normal distribution is always the mean. I said when we do this on our calculator, the inverse norm on your calculator always uses this probability where this area is to the left of the z-score. The area for the critical values is always the area to the right. Inverse norm gives you areas to the left. The critical value is referencing area to the right. So because of symmetry, we've got the right number, but it's got the wrong sign. So this critical value would actually be 2.33. Another question was, well, couldn't we just use our calculator with the inverse norm and type in the area to the right? And the answer is absolutely. Instead of using 0.01, the area to the left of the z-score is 0.99. That gives you the actual, that's why we draw the pictures. A brilliant student just said, just look at the picture. And if it looks like it doesn't make sense, then just know that your sign is wrong. The 0.99, this area over here is 0.99. This critical value, this is something unique to critical values. Critical values subscript, the subscript that belongs to the critical values, is the area to the right of the z-score. It's always the area to the right because we want this to be a positive numbers. Critical values are always positive. Inverse norm on your calculator uses the area left of the z-score for the probability. But remember, always draw the picture because the picture will tell you or indicate to you if you've got a reasonable number. Is it positive? Is it negative?